Hello, we already explained that electrolyte concentration cells with transference reversible to cations we completed, and now we discuss here reversible to anions. Example with reversible to anions. Example is given here. Here in that case, in previous case, hydrogen gas electrode is there, platinum H2 at both side, and that electrolyte concentration is same as here also, and in that case also HCl electrolytes are there. Electrode here changed, that is instead of platinum gas electrode, here electrode used is silver coated with silver chloride, that is metal ion or metal sparingly salt electrolyte. Silver rod is coated here with its sparingly soluble salt, that is silver chloride, and that rod is dipped in HCl at one side having activity A1, and in another side HCl electrolyte having activity A2, and in that solution also same electrode is dipped, that is silver chloride electrode. Here if we consider electrode and solution, that is electrolyte solution, then Cl minus ions are common, and therefore this is example of electrolyte concentration cells with transference, that two solutions are separated by single line. Single line means semi-permeable membrane, which allows that passage of ions, and therefore two solutions are here considered as a in direct contact with each other. Therefore this is example of electrolyte concentration cell with transference reversible to anions, because in electrolyte and electrode Cl minus is common, therefore reversible to anions. Consider electrode reactions at anode oxidation, that is simple oxidation is here. Cl minus is converted to Ag plus Ag solid is converted to Ag plus 1 electrode, 1 electron. It's a simple oxidation, but where that oxidation takes place? At left hand. At left hand, that silver solid is dipped in HCl, where availability of Cl minus ions are there. Therefore, as soon as because of oxidation Ag plus is formed, as soon as Ag plus is formed, it immediately combines with Cl minus, which is freely available in that solution, and there is formation of AgCl precipitate, and therefore combined reaction is written as here oxidation reaction, that is Ag solid plus Cl minus having activity A1 is converted to AgCl solid plus 1 electron. Then at cathode reduction is there. How that reduction takes place? Here also simple reduction, that is simple reduction reaction, Ag plus 1 electron, that gives Ag solid, is a simple reduction, but Ag plus is not freely available at right hand side. Ag plus is not freely available, then it is in the form of AgCl. Therefore, AgCl plus 1 electron, that convert to Ag solid plus Cl minus having activity A2. At this side, solution having activity A2, therefore. Then net cell reaction by cancelling common factors. Net cell reaction is Cl minus having activity A2, Cl minus having activity A1 is in equilibrium with Cl minus having activity A2. This is the material transfer takes place because of electrode processes taking place in that cell, and this is say equation 1. Then during 1 Faraday passage of electricity through this cell, there is a transfer or movement of ions from one solution to another. How that ion movement takes place here? In this case, at right hand side, what is the situation? At right hand side, if we consider left hand side first, at left hand side, oxidation is there. How that oxidation takes place? Ag solid is converted to AgCl. AgCl formation is there in oxidation. AgCl formation means that Ag plus formed combined with Cl minus ions from solution. Therefore, Cl minus ion concentration in this solution, in this A1 activity solution, Cl minus ion concentration decreases, which leads to increase in concentration of H plus. H plus ion concentration increases, and therefore that H plus ions migrated towards adjacent solution of HCl having activity A2. At the same time, what happened here at right hand side? Because of reduction, what is the situation? See here, because of reduction, Ag plus ions neutralizes, converted to Ag solid, and therefore there is formation of new Cl ions, Cl minus ions. They becomes as a unneutralized, non-neutralized Cl ions, and therefore negative charge, that is Cl minus ion concentration at this side increases, at right hand side increases, and they migrate towards adjacent solution having activity A1. Therefore, we can write this material transfer reactions as this. Here we write T minus is equal to 1 minus T plus. We already known that transference number of cation plus transference number of anion is equal to 1. That is T plus T minus small t, small t, which indicate transference number of cations, and if T minus is there, transference number of anions, and that is always equal to 1. That one is standard equation, we already known at SY level. We studied that. Then T minus plus T plus is equal to 1. Therefore, T minus is equal to 1 minus T plus. And therefore, instead of written as a T minus equivalent of Cl minus, here what is considered? 1 minus T plus, which is nothing but equal to T minus. 1 minus T plus equivalents of Cl minus ions having activity A2 are converted into, are migrated towards 1 minus, or are equilibrium with 1 minus T plus Cl minus having activity A1. Cl minus is migrated here from solution having activity A2 to A1. Therefore, here we written same as A2 to A1. Therefore, this one is considered equation 2. At the same time, there is passage or movement of H plus ions from solution having activity A1 to A2. Therefore, T plus equivalents of H plus having activity A1 are here equilibrium to T plus equivalents of H plus having activity A2, because here see H plus migrated from A1 to A2. Therefore, that equation is considered. Then overall process is a sum of 1 2 3, sum of 1 2 3, sum of 1 equation 1, sum of equation 2, sum of equation 3. By considering that LHS and RHS terms and neglecting common factors, we here got equation as a T plus HCl having activity A1 is equilibrium with T plus HCl having activity A2. This is a final equation by cancelling common factors and rearranging that RHS and LHS terms. Then applying Nernst equation to this final equation, we got E cell is equal to E standard cell minus 2.303 RT upon NF log of E2 upon A1 raised to T plus. Here we know that E standard cell for concentration cell is 0. 2.303 RT upon NF is always at 298 Kelvin temperature. It is 0.0591. By substituting that, we got here equation as E cell is equal to T plus into 0.0591 into log of A1 upon A2. For spontaneous cell reaction, A1 must be greater than A2. And for univalent electrolyte, that activity is equal to M1 raised to 2 into gamma 1 raised to 2 and M2 raised to 2 gamma raised to 2. Overall, M1 gamma 1 upon M2 gamma 2 raised to bracket raised to 2, and therefore that 2 are rearranging for univalent electrolyte. This above equation becomes E cell is equal to 2T plus into 0.0591 into log of M1 gamma 1 upon M2 gamma 2. We already discussed that yesterday, that's cell reversible to cation. In that case, here 2T minus is there. Now, today here we discussed cell is reversible to anion, and in final equation 2T plus is there. Remember this difference. That is E cell is equal to 2T plus into 0.0591 into log of M1 gamma 1 upon M2 gamma 2. By using this equation, we can calculate E cell, EMF of cell for electrolyte concentration cell with transference reversible to anions. Remember that. Thank you. Try to solve some here examples given on basis of this type of equation or this type of cell. In problem, you first see the type of given cell. From out of 6 types, we already discussed that for 6 types cells, you in problem which type of cell is given, and there are 6 different equations, 6 type of EMF equations. For each type of cell, EMF equation is different. You select from that type. You first choose the type of cell given, and you choose for that cell EMF equation, correct EMF equation, and by using that EMF equation you can calculate EMF for any given concentration cell, that may be electrolyte concentration cell, That may be electrode concentration cell. Thank you. Tomorrow we discuss last part of this topic, last point of this topic, this unit, that is liquid junction potential. Thank you. We stop here.